All right, welcome everyone to the fourth PyDataTT meetup. Before I introduce today's speaker, let me first introduce myself. I'm Rajiv Ratan, one of the PyDataTT co-founders. And before we begin, I'll read the code of conduct for today's session. So just to be quick, be kind to everyone, don't insult or put down anyone. It's a professional environment, so we won't tolerate any harassment, sexist, racist, or exclusionary jokes and language that aren't appropriate for PyData. All communication is expected to be for a professional audience and include people of many different backgrounds. So no sexual language and imagery will also be allowed, will not be allowed. So yeah, we just want to share a harassment-free environment, and we want to welcome everyone to this friendly community where we share our love for Python and data science. So today's speaker will be Shiva Ramoudith, who will be presenting an introduction to big data processing with Dask. So Shiva, if you want to begin, you can just introduce your topic and yourself and start the presentation.
Sure. Okay, so good afternoon, everyone. My name is Shiva Ramoudith, and today my presentation is entitled An Introduction to Big Data Processing with Dask. Okay, so a brief overview of what we're going to cover today. We're going to introduce data analysis as well as big data concepts. Then we're going to go through an introduction to Dask, and this is more in terms of how it works underneath, under the hood. Then we're going to go through a brief tutorial on Dask using a Google Colab, and afterwards we'll have a question and answer session. Okay, so before we get into Dask and whatnot, let's define some terms, right? So what is data analysis? Data analysis is the process of cleaning, analyzing, interpreting, and visualizing data to discover valuable insight that drives smarter and more effective business decisions. You'll often come across the term data analytics with regard to the business context. And this essentially is the science or discipline that encompasses the whole process of data management. Not only does data analytics include data analysis itself, but it also involves data collection, organization, storage, tools and techniques used to deep dive into data, right? As well as some visualization tools. So data can be classified into two types, and this is structured and unstructured. So structured data is highly organized and formatted so that it's easily searchable in, for example, being a relational database. So you can think of it as data that fits neatly within fields and columns and so on. Now, on the other hand, unstructured data has no predefined format organization, thus making it much more difficult to collect, process, and analyze. And some examples of unstructured data include text, video files, audio files, social media posts, and the list could go on and on. So some advantages of data analysis. So by analyzing data, a business can discover insights about their customers. The business could also deliver more effective product strategies. The business could detect potential growth opportunities. The business could develop more effective product strategies and as well remove reliance on experience or intuition in terms of making important decisions. So some common data analysis tools that kind of come to mind nowadays, there's Tableau, there's Microsoft Excel, Microsoft Power BI, Google Data Studio, and then there's Pandas and R, to name a few. So this gets us on to know actually what is big data. So big data is a larger, more complex data sets, especially from a variety of data sources. These data sets are so voluminous that traditional data processing software just can't manage them. These essentially are massive volumes of data that can be used to address business problems you wouldn't have been able to tackle with normal size data. So again, big data could be both structured and unstructured. It contains a greater variety, arriving at increase in volume and with more velocity. And this is essentially known as the 3Vs. Now, big data is so large in size and complexity that, as I mentioned before, no traditional data management tools can store, process it efficiently. And the origin of these large data sets kind of goes back to the 1960s and 1970s. And this was around the time of when we saw the introduction of the first data centers and the development of the relational database. So some advantages of big data. So since there's more information, this makes it possible for us to gain more complete answers to questions. And more complete answers to questions means that there's going to be higher confidence levels in the data, allowing for more approaches involving decision-making, early identification of risks to product and services, and the improvement of operational efficiency. So just to give an idea of some statistics, and this is essentially what you could call big data, right? So the first one, the amount of data generated by Facebook on a daily basis is estimated to be around 4 petabytes. And 1 petabyte is equivalent to 1,000 gigabytes. And that's on a day, right? The second one, Google gets over 3.5 billion search requests daily. This is as of 2020. WhatsApp users generate up to 65 billion messages daily. 95% of businesses cite the need to manage unstructured data as a problem for their business. And this was with regard to last year, a survey done last year. And in 2017, the economists claimed that data has replaced oil as the world's most valuable resource. So the thing is now, can we use the previously mentioned tools in doing big data analysis? So I have some points listed here with regard to some software tools and some limitations of them. So Microsoft Excel, first one, there's a maximum of, I think, 1 million or close to 1 million rows and approximately 16,000 columns. So anything beyond that, Excel will crash or hang and whatnot. There's Google Data Studio, which is quite good, but one caveat I came across online is that a lot of people mentioned that there is only access to a left outer join, and the rest of joins are not supported by Data Studio. In terms of pandas, it's quite common. Data frames are kept in memory in pandas, so anything that's beyond the size of memory is going to result in out-of-memory exceptions and failure in that regard. And in terms of Power BI and Tableau, they do incorporate some aspects of big data processing, but some people reported that there are instances where the software crashed a bit. So I'm not too sure with that one, but that was something I came across that I was quite kind of widespread online when I kind of researched Power BI and Tableau. Okay, so now on to some common big data tools, right? So there's Apache Spark, right, and Apache Hadoop. So Hadoop is an open source framework written in Java that allows us to store and process big data in a distributed environment across various clusters of computers using simple programming constructs. So to do this, Hadoop would use an algorithm called MapReduce, which essentially divides tasks into small parts and assigns them to a set of computers. Hadoop also has, along with it, its own file system, which is known as HDFS, and it's based on the Google file system. And HDFS is designed to run on low-cost hardware. So the second thing now is Apache Spark. So Apache Spark is, again, another open source framework. It's distributed in nature and allows for cluster computing as well. Spark is essentially a data processing engine developed to provide faster and easier to use analytics than the MapReduce using Apache Hadoop. Right. There's also, this is more recent, there's also Rapids. Rapids is essentially a suite of software libraries for executing end-to-end data science and analytical pipelines entirely on the GPU. There's Apache Hive, and this essentially is more along the line of some data warehouse software, and it's built on top of Apache Hadoop, providing the opportunity to do data queries and analysis. And the Apache Hive would give us an SQL-like interface to query data stored in various databases and file systems that integrate with Hadoop. Then we go on to Blazing SQL. Now, Blazing SQL is, I use it already, and I would say it's pretty nice. And essentially, it's a GPU-accelerated SQL engine built on top of the Rapid system. And Rapids, again, just to give some insight, is based on Apache Arrow, columnar memory format, and cuDF, which is a GPU data frame library for loading, joining, aggregating, filtering, and essentially anything to do with manipulating data. Lastly, we have Cloudera, which is essentially a platform that provides a scalable, flexible way to manage rapidly increasing volumes and varieties of data in more or less the enterprise sphere. And Cloudera products and services, the solutions actually enable you to deploy and manage Apache Hadoop and related projects to analyze your data and keep that data secure and protected. Okay, so again, as based on the title, today I'll be discussing some things based on Dask, right? So Dask, again, just to dive a bit deeper, it's a flexible computing library for parallel computing that's based in the Python programming language. And essentially, it is a native parallel analytics tool designed to integrate seamlessly with NumPy, Pandas, and sklearn. And what it allows us to do is that it orchestrates parallel threads or processes for us and helps speed up our processing times. Just to give some more insight as well, Dask seeks to address the following points. So essentially, the first main point is that if a data set, my bad, does not fit into memory, this is one instance where Dask is able to help you. And in the event that we need faster processing and computation, Dask will also help us there with the parallelism it offers. Right, so an overview of Dask in itself, right? So essentially, you could think of Dask as essentially an API, right, that allows us to interface with the system itself, how it's created, and then in doing that, certain things are done in parallel and so on. So there are collections, and there's a task graph, and then there are schedulers. So the collection essentially provides the API used to write Dask code, right? And from that, so we see that there's the Dask array, there are Dask data frames, Dask bag, Dask delayed, and futures. Today we'll be kind of more or less focusing on the first three. Then there's the task graph. So the collections now would then create the task graph, which are directed in nature. And essentially this graph is going to define how the computation is going to be performed in parallel. So now, after the task graph has been generated, Dask needs to execute these tasks on parallel hardware, and the computation is performed on a cluster which comprises a scheduler and a certain amount of workers. Now, the scheduler could be distributed in nature, happening across multiple machines, or it could be on a single machine, as you could see with the example I'll show in a few. Right, so that's a bit of a dive into some collections within Dask. So the Dask data frame essentially is a large parallel data frame composed of many smaller pandas data frames put along the index to facilitate a subset of the pandas query syntax. There are Dask bags, which store and process collections of Pythonic objects that are unable to fit in memory again, and operations such as map, filter, fold, etc. implemented. And then there's Dask arrays, which implement a subset again of the features of NumPy and the array interface using blocked algorithms. Essentially, this would allow us to cut up or take a large array and split it up into many smaller arrays. Right, so the question is now, why have I chosen Dask today, right? And a few points for this as well. So Dask has a familiar API. So analysts often use tools like Pandas, sklearn, and NumPy, and the rest of the PyCon ecosystem to analyze their data on their personal machine. And they they like these tools because they're efficient, they're intuitive, and widely trusted. So the thing is that when they choose to apply the analysis and so on to larger data sets, they often run into problems, right? So the API that Dask provides is quite very much similar to that of sklearn and NumPy and what have you. So it's very familiar in that regard. Dask can scale out to clusters. So as data sets and computations scale faster than CPU and RAM, we need to find ways to scale our computations across multiple machines. So Dask addresses the following concerns. So how do you have computers talk to each other over a network? How and when to move data between the machines? How to recover from machine failures? How to deploy on an in-house cluster? How to deploy on the cloud? How to provide an API to the system that users deem intuitive. Right. So again, while it's possible to build these systems in-house, right, and many, I guess, software exists that is actually in-house, right? Many organizations increasingly depend on solutions developed within the open source community. So these tend to be a bit more robust, secure, and fully featured without being tended by the in-house staff. So Dask essentially solve the problems I mentioned a bit above. And it essentially figures out how to break up large computations and route them efficiently onto distributed hardware. So typically you'd find Dask being run on 1,000 machine clusters to process hundreds of terabytes of data efficiently within a secure environment, right? Dask can also scale down to a single computer. So in some cases, a massive cluster is not always the right choice. Today we have a lot of laptops and workstations that are quite powerful, and if used correctly, they could actually handle a lot of data thrown at them, right? And a modern laptop might have a multi-core CPU, around 32 gigabytes of RAM, flash-based hard drive storage, so which essentially allows for streaming through data a lot faster than hard drives and what have you. So as a result, Dask could actually empower analysts to manipulate 100 plus gigabyte data sets on their laptop or on a workstation without bothering with the cluster at all. And lastly, Dask provides support for complex applications. So some parallel computations are simple and just apply the same routine to many inputs without any kind of coordination. And these are fairly simple to parallelize within any system. But somewhat complex computations can be expressed with the map shuffle reduce pattern popularized by Hadoop and Spark. And this is often sufficient to do most data processing and cleaning tasks. However, with more complex parallel computations, we find that some of them don't fit into these previously mentioned paradigms. So they are a bit difficult to perform with these traditional technologies. So Dask, again, allows us a bit more flexibility in terms of orchestrating complex parallel computations. Okay, so on to this next slide. So there's Apache Spark and there's Dask, right? And Spark is essentially, if I'm not mistaken, one of the most popular distributed computing tools for data sets. And it is essentially a very dominant big name in the data analysis field today. So Dask has a lot of elements that appear to kind of intersect with the space that what Dask provides. And there are a lot of questions that's commonly asked. How does Dask compare to Spark? Okay, so typically, Dask is a bit smaller and lightweight when compared to Spark. Again, Dask was originally designed to complement other libraries with a level of parallelism. Dask is typically used on a single machine, but also works good on clusters. And Dask has an advantage for Python users because it itself is a Python library. So serialization and debugging tend to happen a bit more smoothly as opposed to Spark. In terms of scale, both of them can actually work from single nodes to 1,000 node clusters. I mentioned before that Spark is a bit older, so it was introduced in 2010. And again, it's very dominant and well trusted in the big data enterprise world. And Dask is a bit younger. It came out in 2014. And again, it essentially is an extension of the well-trusted NumPy, Pandas, sklearn, Jupyter Hub, Jupyter Notebook sort of stack. So this brings us to now reasons why one would choose Spark, or what reasons why one would choose Dask. So if you're looking at Dask, right, you tend to have preference to Python or native code, or have larger legacy. Wait, I think I mixed this up. Sorry. So this is essentially reasons for choosing Spark, right? So you're gonna have, so if you tend to choose Spark, you're gonna have mostly JVM infrastructure and legacy systems. You want an established and trusted solution for your business. That's Spark. You are mostly doing business analytics with some lightweight machine learning. And again, Spark is an all-inclusive framework, right? In the case of Dask, your use case is a bit more complex, or it doesn't cleanly fit the Spark computing model. You want something that's more lightweight to transition from local to cluster computing. And you want to interoperate with other technologies and don't mind installing multiple packages. So Dask is a bit more on the kind of bleeding edge sort of things. And Spark is a bit more concretized for enterprise level stuff. Okay, so that was, I guess, a bit of explanation there. Let's get a bit of a demo showcasing the benefits of Spark and how it actually operates. Right, so just for this tutorial, prerequisites, you're going to need a Google account. And once you have that account active on your machine, you can access the following Google Colab link. Right, so I'll just probably paste this here in the chat for everyone. Okay, so I'll stop sharing my screen and I'll share the tab with the tutorial. Okay. Okay, so everyone could see the new screen, right? Just confirming. Okay, so I assume everyone has access to tutorial and they could see my screen. Okay, so again, I'm doing the demo today with Google Colab. I chose this particular tool because it's quite easy to share and distribute code and have it run on multiple instances throughout, right? So once you have a Google account, you could actually download the notebook and run it as though if it was your own notebook, right? So it's quite useful for performing experiments and so on. Okay, so again, the first thing we do typically is essentially ensure that the requirements are satisfied. So I just installed something concerning Dask itself here, Dask data frame. And then I think I went on to import a lot of the necessary tools I'll be using for the tutorial today. So this particular section here goes to give an example of the Dask array versus a NumPy array. So here I've generated a NumPy array of random numbers. I think it's around either 1 billion numbers if I'm not mistaken. And I wanted to show very simply here the differences in processing between using this, doing a computation with Pandas, doing a computation with NumPy versus doing a computation with the Dask array. Okay, so I've created the Dask data frame here. So essentially, the code has already been run, so I won't really waste time redoing anything at all. Okay, so I've generated the array here, and that's a defined in for NumPy. Now, with regard to Dask, I'm going to pass that array to a function in Dask called from array. And what this would do is that it's going to take a NumPy array and split it up into chunks so that Dask could process certain aspects of it quite efficiently. So I'm just specifying here a number of chunks being 20. So it's going to take that, I think, 1 billion size array and split it up into portions, 20 portions of equal size. And the array underscore Dask is the Dask array here. Just some things to note. So just to show an example of the performance difference with time, the user time that's defined here, when I do the computation, denotes time spent on non-kernel tasks. And the system time denotes time spent on kernel processes. Essentially, the wall time as well would give us a better idea of, okay, the cell has been started and it took X amount of milliseconds or what have you for the cell to be completed. So we'll look at more or less the wall time to get an idea of performance across the board with Dask and NumPy. So again, just a note, Dask objects are lazily evaluated. So operations like mean and sum and so on, they build a graph of block tasks to execute. And then only when you're ready to compute, you obviously call the compute function, which is going to trigger the actual computation. Excuse. So here I have the result here using Dask, and this is the result here using NumPy. So essentially what I've done, essentially just take that array that I generated, multiplied everything by 2, divided it by 5, and then I decided to go and find the sum of all those numbers that have been multiplied by 2 and divided by 5. And it took around 446 milliseconds. Right, so onto Dask, again, as I mentioned before, we need to call compute to actually trigger the actual computation. So in this line here, or this cell, I define exactly what I want done. And then afterwards, I could call result.compute to go ahead and execute the computation, right? And our next interesting thing that we could do with Dask is actually plot or visualize the structure of the graphs to see what is being done, right? So again, I think I defined a size of 20 for the chunk. So essentially what it does is going to take that entire data frame and split it up into multiple chunks, right? But 20 chunks to be specific, right? So we have chunks ranging from 0 to, I believe it's 19. And afterwards, it's going to perform the multiply operation on each particular chunk. It's then going to do, I believe, division. Then it's going to do a sum on all the objects within that particular array. And then now it's going to combine those into a result. And then it's going to combine multiple results into a partial result. And lastly, it will take those partial results now and have it as a result for the entire array. And this is how Dask more or less works in the background. So a bit back onto the computation time. So in terms of speed, the wall time for a NumPy array, this computation here took 446 milliseconds. And with Dask, it took 311 milliseconds, right? Now, I must mention that with Dask, there's a bit of overhead in terms of generation of the graph and so on. So in some cases, especially for small data sets, you would find that NumPy will perform a bit faster than Dask. But when you tend to scale out and go beyond the size of memory, this is where we kind of get the benefit of Dask showing up here. Right, so it's a bit fairly close in this case. This has to be modified, so my bad there. Right, so let's give another example now to kind of show a bigger difference in processing time between NumPy and Dask. So let's define a function. Multiply 2, add 1. It's going to sleep for 5, I believe it's 15 nanoseconds. And then it's going to compute whatever value you passed in, multiply by 2, and add 1 to it. Just a very simple operation, right? So let's now time this operation using NumPy convention. So we're going to create a NumPy array. And for every value within the array, we're going to compute the result of applying the multiply 2 and add 1 function. And then we're going to add those results to a total, okay? And this is the value here. So you can see that here. So when I ran this, the wall time again was 5.02 seconds. It's quite fast, right? And in terms of Dask now, what we do is more or less the same convention, but the line that changes more or less is the third line in particular. So this here is we say Dask.delayed, and we pass in the function, and then any parameters to the function go right after it in parentheses as well. And then the result now is taken and added to your total. So it's almost the same convention, but it does it very much starkly different. So here I visualize what each call to Dask.delayed passed in with the function does. Essentially, it would take an element and pass it to that multiply add one function and return a result. So when I'm finished with that now, I could actually take the value total and do a compute on my total. So again, total is essentially a combination of multiple res values, and each res value is a Dask delayed function, which is going to ingest the multiply to add one function, and then with that function, we pass it in the value as the parameter for that particular function. So here now, again, this is a very large graph, but you could see what's going on. I believe so. This is for 500 numbers. For 1,000, it was much larger, and you could see the orchestration that kind of goes on in the background for this to happen, right? So it's a lot of elements being added to the graph, and then finally we get to the result where we have the total being generated, right? So just to go back a bit to the runtimes, you'll notice that the runtime for Dask actually was 2.55 seconds, and I think with NumPy was 5.02 seconds. So again, this was a bit to illustrate an instance where we had to wait a bit. So if we had to wait, because of Python and how it inherently is, because of that global interpreter lock, we have to wait for every single call with every single value passed to this multiply to add one function to finish, right? So that's why it takes almost double the time. But with Dask, actually, because it could parallelize the calls across the processes of the machine, it is able to do it a bit faster. So again, if I scale out to a very large array, you'll see a massive difference between the time for Dask and the time for doing the same computation on a NumPy array. Okay, so that's it there. Okay, so now a bit onto the Dask data frame versus the Pandas data frame, right? So I came across this. I mean, it's very common on New York City taxi fare data set. And essentially, it was around 5 gigabytes. So with this demo, or with this section of the demo, actually, I wanted to show you the differences between getting it to work with Dask as opposed to a Pandas data frame. Okay, so again, this first cell here contains the link and the setup code to just download that particular zip CSV file from my Google Drive, and it will also work on your instance as well. Okay, so after I've downloaded that particular file, I extracted it. So after extraction, I believe that file was around 5 gigabytes in size, right? So that was when I attempted to load this file to the Colab instance with Pandas. So upon running it, you'll find that your instance will crash, right? So because Pandas inherently, it loads everything into memory, that 5 gigabyte file is too large when it's in memory, so it's gonna crash your instance and fill up the memory. Okay, so if you're using Pandas, let's utilize something called chunking, and this is available within the Pandas library to essentially read in this large data set, right? So what you would do is the same typical Pandas read CSV function, but you pass in that file name as well, but you specify a chunk size. So I've specified here a chunk size of size 1 million. So what that does, it splits that entire read operation into a series of chunks, okay? And each chunk is of size 1 million. Now, upon seeing what type of variable this is a text file reader object within the Pandas library. So upon calling every element within this chunk variable, what it's going to do is going to give us access to that particular section or chunk from the Pandas data frame in memory. So I have this defined in the next cell here, where I define a chunk list, and this is going to contain all my chunks, right? Now I've defined a chunk preprocess function, which is essentially going to take in one chunk of data. Again, it's 1 million in size. And again, because pandas can't store the entire data frame in memory, I'm just going to extract the passenger count feature, right? So essentially from here on out, I'm going to be using this passenger count feature just to get a sense of some certain metrics for the data, right? So now for every chunk within, again, df chunk, I'm going to append to that chunk list now, and I'm going to call now chunk preprocess, and I'm going to pass in that chunk object there again. So what it's going to do, it's going to take every chunk and then restrict that chunk alone to a list of passenger counts. So at the end now, I could actually call pandas.concat. What I would do, it would take every data frame in my chunk list array and combine it into one pandas data frame, right? So from that now, we could actually get a portion actually of that train.csv into memory, right? And then doing a df.mean is quite simple. Again, it's quite fast, right? But again, let's just say in the case that the data set was so large that even if I just removed the passenger counts alone, it could have still failed because, again, of the size, right? So this, again, is just to show you how we can kind of get around a large data set. So if in the case you want to analyze certain features from a data set, if you could work with chunk, it's much appropriate to work with. It's much more easier and a bit faster to work with. In the event of Dask now, it has the ability to work with out of memory data sets, but again, there's a bit of a cost associated with Dask, right? So let's try Dask. So again, trying Dask. So Dask df now is defined as my object after reading that train.csv file again, right? So I've assigned it here. I just display ahead, so you can see that Dask df is able to load it. I'll say load it in quotes, efficiently and effectively. So what it does, how it operates is that Dask doesn't do any computation until you specify, right? So it's a bit delayed in nature, right? So do not Dask df.head. I can see, I'll take a bit of a peek into what the data set looks like. It has a timestamp for when this particular transaction occurred, sense of the fair amount and what have you, pickup times on latitude and longitude coordinates for each trip in NYC for some period of time. So checking the shape of this, I think it's 55 million rows we're looking at here with this 5 GB file. Okay, so let's just go ahead and convert that particular key feature into a datetime object. So I say dd.toDatetime, and I'm passing the particular feature here. And then afterward, just double checking here, I realized that, it's actually set to now a datetime object here. So what I'm going to do now is essentially do a bit of a computation to show how Dask is able to operate here. So I'm just checking here very simply to see the difference in the mean passenger counts for the first half and second half of 2019. So probably as we get along to the Christmas season, we would find that we tend to have a lot of more passengers taking taxis. So the passenger mean count for each taxi might be a bit higher, right? So in actuality, it's not that much higher based on this data here for this year, 2009, but it's marginally higher. So 1.69 as opposed to 1.68 passengers per taxi. Not really much difference there. But in terms of runtime, actually, the computers took about 2 minutes using Dask, right? Whereas if I had this with pandas, it would be done much faster. But again, the caveat is that if I were to use multiple features from my pandas array, from my data set, pandas won't be able to handle it. So this is where Dask is able to come in and parallelize a lot of things for us and make it a bit much easier. So again, with Dask, you don't have to worry about setting up different chunks and pre-processing your data to make it smaller and what have you. So yeah, so that kind of is more or less it. The little small tutorial on how Dask operates. So I think I could stop sharing my screen. Yeah. Now I'll share back my slides. Okay, so that kind of brings us more or less to the end of the session today. So before we close, see that my screen sharing is paused. Okay, right. So yeah, this is the final slide, anyways. And so before we close, I'll mention some further things that is capable with Dask, right? So again, with Dask, we kind of saw the difference that and the benefits it provides, especially when we deal with out of memory data. So anything that's bigger than the size of memory, this is where Dask would benefit us. I'd recommend that in the case of your data being able to fit into memory, you could utilize pandas, and that's completely fine. And it'll work a bit faster than Dask. But again, if you're going out of memory, I recommend Dask for that. In terms of integration with NumPy, with sklearn, the only way you'll really see that happening is when it tends to scale across multiple machines. So you can actually configure the Dask scheduler. I think the scheduler could either be set to either single machine or distributed in nature. So let's just say, for example, you have a series of machines online and they're connected in some way via a network or what have you. If you spin up a Dask distributed scheduler, right, or that particular term there, you can actually utilize multiple machines across the cluster to do specific computations. And again, the benefit is here when we can't fit in memory, this is where Dask is able to provide us that benefit. Dask is also able to provide us that benefit when we're using the framework called Rapids. So again, the example I showed here today was essentially using Dask on the CPU. But if you look at Rapids essentially is a very nice framework. It was introduced by NVIDIA quite recently. And what it does, it allows us to exploit the power of the GPU to do a lot of numerical computing as we do it with typical pandas on the CPU. But with Rapids, it's much faster. So the way Dask would come in with Rapids is that, again, it will allow us to scale across multiple GPUs to exploit the power of all those GPUs for our particular computation. So again, that would bring me to the end of my presentation today. Thank you everyone for listening, and I hope it was insightful. I guess I could open the floor now for any questions. Thank you.